In this lecture, we will talk about Chapter 10, the earliest hominids. So we'll jump right in to talk about what it takes to be a biped. Upright walking leaves its mark on a skeleton. Species that walk on two legs rather than on all fours have unique skeletal anatomies that can be detected in the fossil record. For instance, in animals that walk on two legs, the head perches on top of the neck, whereas in animals that walk on all fours, the neck comes out of the back of the head. There is a hole in the skull called the foramen magnum, which is the route by which the spinal cord exits the skull. The position of this hole can be used to infer whether the skull sat directly on top of the neck as in bipeds. Likewise, the spine of the biped in animals is S-shaped, so that the head, neck, and hips are all balanced. This results in something called lumbar lordosis, which is in which the lower part of the spine is curved inward, producing the small of the back. Animals that walk on all fours have more of an arched C-shaped spine. The shape of the human pelvis is also unique. Chimpanzees and other apes have a tall, thin top part to the pelvis, which is called an ilium. The ilium in humans is short and stout, or flattened. It is also rotated to the side of the body. As shown in this image, the fossil hominin of Australopithecus afarensis also had a short and stout pelvis, like that found in humans. This suggests that Australopithecus was a biped. Why does the shape of the pelvis tell us that an animal walks on two legs rather than four? Animals that walk on four legs do not have as much of a balance problem. However, bipeds do. As illustrated in the cartoon on the slide, each time you take a step, you have to lift one leg completely off the ground, forcing your body to balance for a short time on a single leg. When this happens, the force of gravity wants to pull your entire body away from the weighted leg. This twisting force is called a torque and should cause you to wobble from side to side when you walk. However, we walk in a much more balanced and coordinated fashion than that because of muscles in the hip called abductors. These muscles contract on the same side as the weighted leg when the opposite leg is lifted to balance the torque created during one-legged stance. Try this yourself after this lecture. Put your hands on the side of your hips and you'll feel muscles contract when you're standing on one leg. The flattening and widening of the pelvis, especially where the abductor muscles attach on the ilium, increase the leverage and therefore the efficiency of these muscles. The neck of the femur, the leg bone that fits into the socket of the pelvis forming the hip joint, is also quite long in bipeds to align the attachment of the abductors on the femur to the attachment of the wide flaring ilia. The femur of bipeds also has an uneven thickness of dense cortical bone in the neck of the femur, whereas chimpanzees and gorillas have a more even amount of bone to support the wide range of postures they put their hips in during walking and climbing. The knee of bipeds is also quite unique. In order to keep the feet, knees, and hips balanced and aligned with the center of the body, the human knee slants downward and inward. This is something called a bicondylar angle. Importantly, humans are not born with this, and those humans who have impairments that prevent them from ever walking never develop it. Therefore, the presence of this anatomy is a true indicator that the individual must have been walking on two legs. As you can see, both Australopithecines and humans have a bicondylar angle, but the chimpanzee does not. Genetic evidence. So when we're thinking about this evidence of what it takes to be a biped, paleoanthropologists can look at the fossil record to gauge whether or not ancient fossils were in fact bipeds. So one of the earliest fossils that indicates a last common ancestor between humans and chimpanzees would have lived somewhere between 5 and 7 million years ago. One of the first that were discovered was Sahelanthropus chidensis, and it's represented by a really complete, though distorted cranium, as shown on this slide, also several pieces of lower jaw and teeth. This fossil is dated to be around 5 to 7 million, or 7 to 6 million years old. Interestingly, the brain is chimpanzee-sized. However, it had a foramen magnum, which helped to suggest bipedality. There are a couple other early species that are thought to be a common ancestor between chimpanzees and humans, and I highly recommend you reading about those in the book because they could show up in the exam. However, I do want to ask the question, why did bipedalism evolve? The earliest purported hominids did not have big brains, and they presumably could not talk the way that we do, which suggests that bipedalism evolved before large brains. So there are a few different explanations. So one is a feeding adaptation. So orangutans, for instance, will often adopt bipedal postures when they're feeding in trees. Additionally, chimpanzees will sometimes stand bipedally, as illustrated in the image. Others have suggested that bipedalism is energetically more efficient than knuckle walking. However, both of these hypotheses rely on the earliest hominids being chimpanzee-like. And one of the early species, Ardipithecus, challenges that hypothesis. The next one is the thermoregulation hypothesis, and it proposes that bipedalism lowers the amount of solar radiation one is exposed to in intense African savannas. And then one final idea is that bipedalism was favored as a caring and provisioning adaptation. So those who happen to move bipedally may have been able to carry more food and share it with potential mates. So now we're going to move forward a little bit. So from 2 to 4 million years ago, hominids diversified into many different species and perhaps very different genera. So they expanded across Africa, and here we see some robust species and also some more human-like early hominids. So the Australopithecines are one of the best examples of an early ancestor. And for Australopithecines, there are five different species that paleoanthropologists have discovered. We're going to focus on Australopithecus afarensis in this lecture. So it's one of the best represented and best known hominids, and hundreds of fossils have been recovered in 3 to 3.6 million year old deposits in Ethiopia and Tanzania, including the very famous partial skeleton of a female Australopith known as Lucy, which is shown here. Lucy was quite small compared to a modern human, but like us, she walked on 2 legs. And in the exam, you're going to want to know how the name Lucy was determined by the researchers. So that's definitely in your book. In 2010, a 3.6 million year old skeleton of a male afarensis was announced, and in 2006, the skeleton of a 3-year-old was reported. This latter find will be discussed on the next slide. But anyway, the average brain capacity of Australopithecus afarensis was 450 cubic centimeters, slightly larger than the average chimpanzee brain. The face jutted out in an ape-like fashion, and there were attachments on the skull for powerful chewing muscles. So the molar teeth were quite large. Their lower bones also indicate that they were very capable at bipedalism. So in 2006, Zuree Zagad published a preliminary description of a very stunning fossil. This was the remains of a 3-year-old Australopithecus afarensis that lived over 3.3 million years ago. So the skeleton is still being cleaned and studied, but it is already more complete than the famous Lucy skeleton. So this finding allowed researchers to know things about afarensis that were previously unknowable. For instance, could Lucy and her species talk? How could we ever know that? There's a small bone in the throat called the hyoid. Many muscles are important for speech, attached to this bone. So the hyoid has a very different shape in humans compared to the great apes. This bone is almost never discovered as a fossil, given how fragile it is, but it was found with Ch10. The shape of the bone was chimpanzee-like, which should suggest that the vocal language had not yet evolved in this species of Australopithecus. The development of the teeth allowed researchers to estimate that her age at death was about 3 years old. At this age in chimpanzees, the brain is around 90% finished growing. However, with a brain of only 300 cubic centimeters, the Ch10 child had achieved only 75% of her adult brain growth, which is a pattern like that found in humans. So you could see that this fossil had both human-like and ape-like qualities. Moving forward, if we're thinking about all the different Australopithecines that have been discovered, Australopithecus' skulls and dentition were intermediate between apes and humans, as you can see in this image. The Australopiths had relatively large incisors and exhibited a diastema, but had a large jaw and cheekbone. The endocranial volume or brain capacity of Australopithecus was also larger than chimpanzees, but smaller than modern humans. So though Australopiths share these facial characteristics, they lived in a wide variety of woodland and grassland habitats and ate a variety of foods. Also, the anatomical evidence of the pelvis, femur, and foot indicate that they were fully bipedal when on the ground. They had an S-shaped spine in order to balance their weight, and this would be like modern humans shown in this image. Though their lower body indicated they were bipedal on the ground, there's evidence that they were also climbers, which is pretty interesting, and the advantage of this could have been to protect themselves from predators and potentially sleep at night. So even though the fossil record is limited for Australopithecus, there does seem to be evidence that there's also sexual dimorphism in this species, which indicates that there's competition among the sexes. A couple of slides back, or actually in your book, you can see that there was sexual dimorphism in canine size. Their cranial capacity was also quite small, like we've already talked about, so it should not be a surprise to you that they matured more rapidly than modern humans. So that summarizes this chapter, and where we talked about what to look for with bipedalism and some early examples of hominids, which you'll need to be sure to study more in depth in your text.